So far in this course, we have assumed that the MOS transistor works instantaneously. In other words, you apply gate source voltage and immediately a drain source current, incremental of course, develops. But it turns out that in reality that is not quite correct, as one might expect, right. Nothing in the world is instantaneous. The only thing that you can do is, as technology progresses, is that the devices become faster and faster. So, just like how we to derive the low frequency small signal model, what did we say? Well, we write the nonlinear IV relationship between the drain current and uh, uh, the drain source voltage as well as the gate source voltage, and likewise for the gate current, we said that the gate current was 0. So, there was really nothing to worry about, and the drain current was some complicated nonlinear equation depending on VGS and VDS depending on the quiescent operating point. And what we would do is basically increase the port voltages by small amounts and see what the changes in the port currents would be, all right. And consequently, this is simply valid only at very low frequencies. It turns out that the MOSFET is actually a lot more complicated device, and there are a lot of time varying. I mean, if the voltages at the terminal change very suddenly, then you have to actually use the physics of the device and solve for the current in the transistor. So, you will now, if you account for memory effects, the drain current is not merely governed by some nonlinear equation of the gates, the VGS and the VDS. It now becomes a nonlinear differential equation, right, which govern VDS, ID, I mean VDS and VGS and ID and IG also. So, fortunately, however, even if you have a nonlinear differential equation, right, if you only look for changes or the ratio, I mean, if you change the VGS by a small amount and VDS by a small amount, the change in the VDS and the change in the VGS, in other words, the incremental VDS and the incremental VGS can be related to the incremental drain current and the incremental gate current still by a linear network. It just so happens, as you might expect, that now because the transistor is not instantaneous, the incremental linear network must consist of elements with memory. And just like how the details of the small signal model for the low frequency case was derived by differentiating those equations, which are derived based on the physics of the device. Likewise, we have to do that for the MOSFET, right, and that will take us into the realm of device physics, which we are not interested in getting in, right. So, all that we are interested in, therefore, is basically go to the device folks and say, I mean, you know all the physics of the device, please go and calculate these extra elements for us, right, which are basically these elements with memory, which are capacitors, and potentially could be inductors also. But it so turns out that for over large regions of operation, the model for the MOSFET, which includes which models the memory of the transistor, is basically this one. Right, and so this is, so if the source is grounded, then this is grounded. So, this is basically the model for the MOS transistor when when the source terminal is incrementally grounded. So, this is VG, this is VD, right, and this is all these elements are all the memory elements, right, and so this is CGS, this is CGD, and this is CD, I'm going to call it CDB. It turns out, as you all know, that how the MOSFET is made is, the N MOSFET is made, for instance, is that you have some oxide, and that is the source, that is the drain, and that is the gate. Right, and this drain for an N MOSFET, what kind of substrate do we use? P substrate. So, and the drain and N are made with N plus. So, basically you can see that between the drain and the substrate there is going to be a reverse bias diode. So, this is basically that CDB stands for C drain to bulk. Okay, if the source is grounded, then the bulk and the source are shorted, right, and therefore you basically have it goes from drain to source. But strictly speaking, I mean the parasitic capacitance is between the drain and, if the source is floating, I mean is independently controlled, then this is the source, this is the usual RO, and this is GM VGS, and there is a capacitance from drain to bulk. Okay, all right. The CGD physically is coming because of the overlap between the source and the drain. I don't know if you are able to see this in. That is the overlap between the gate and the drain, right. So, the CGS basically is a lot more complicated. It is coming because, not merely because of the overlap between the gate and the source, but also because there is a channel here, right, and that channel basically there is that channel is connected to the source, and therefore it seems reasonable that there is some capacitance between the gate and the, obviously there is parallel plate capacitance between the gate and the channel, right, but the channel is connected to the source electrically. So, therefore, it seems reasonable that there is some capacitance between the gate and the source. What that capacitance is, again, you know, remember that this channel is actually pinched off at one end. So, clearly, you know, all the field lines from the gate are not basically it is not a uniform channel, and therefore it is kind of wrong to expect that the gate source capacitance will be simply the parallel plate capacitance between the gate and the channel. To actually get a to do this properly, you actually have to get into the device physics, and it just so turns out that after all that, the CGS in saturation, I mean, clearly these are incremental parameters. So, what comment can you make? Like all incremental parameters, they must, all incremental parameters depend on what? Depend on the operating point, right? And so, all these capacitances also in principle must depend on the operating point. It so turns out that in saturation, CGS happens to be 2/3 Cox times W times L, right. Cox is the gate capacitance per unit area, and W and L are of course the width and the length of the, all right. Similarly, CDB, right, is it simply the reverse bias capacitance between the drain and the bulk, right. And clearly, you know, if you have done a basic device physics class, you know that a reverse bias junction has a capacitance which changes with the voltage, but for all practical purposes, you basically assume that it is constant and more, right. And CGD again in saturation is basically due to the overlap between the gate and the drain terminal, and is expected to be somewhat smaller than CGS. So, but to get exact values of this, basically you have to you have to know the device geometry carefully and then do the device physics properly. So, fortunately, as a circuit designer, all these things are modeled. So, when you run a computer simulation, these things are properly accounted for if the modeling is done right. So, so again, as usual, we use this as a black box and then move on. Correct. All right. So, with this background, now we need to go back to all the circuits that we have done, right, and see the effect of these parasitic capacitance on the performance.